All right, can y'all text me to let, or put in the chat to let me know if it's actually going live? So it looks like there's about a 10 to 15 second lag in the video on my end. So kind of keep me informed in case you're having issues. All right, what questions you got for me this morning? So for alkenes, when you have a diene or a triene, honestly, I haven't seen a lot of people talk about using the EZ for that. I think the EZ only works for simple alkenes, but when it comes to the dienes, I haven't seen anything about it. So short answer is I don't actually know how to name them if you've got like dienes or trienes. My guess is it's probably like the RS configurations where you have to put a number beside which E and Z you're talking about, but it's kind of outside the scope of this course. DielsAlder synthesis for discussion board. I cannot figure out how to connect the starting molecule with ethylene. So DielsAlder is one of those, as soon as it clicks with you, it's really obvious how to do it, but it does take a while to see it. So in its simplest form for DielsAlder, we've got a diene, and it has to be a conjugated diene with a dienophile. Now, the mechanistic arrow books like to give is this double bond kicks up, bonds to this carbon, this double bond kicks down, and this double bond kicks over. And so what we get with DielsAlder is a cyclohexene. Now, the reason I don't like how your book does this, it's much better, especially if you can do it color-coded, which if you look at my online notes, it's actually color-coded. The way I always keep track of DielsAlder is I use a numbering side for the diene, and I use a letter side for the dienophile. So let's call this carbon 1, 2, 3, 4, and the ethylene alpha and beta. So when you do this reaction, this is where carbon 1, 2, 3, and 4 are. They're connected to this double bond. So the double bond will always end up between carbon 2 and 3, and the alpha and beta will be on the opposite side from the double bond. So when we start predicting DielsAlder reactions, or when we try to reverse engineer them, what we have to look at is what's attached to the alpha and beta. So let's say we've got a cis-ethylene, so a cis-2-butene, and let's say for our diene, we've got a methyl group hanging off. And then we've got a methyl group hanging off of carbon 1. So to predict a DielsAlder reaction, always start with your cyclohexene. This, you know you're going to make this by DielsAlder. Now, when you finish with DielsAlder, this is always carbon 1, 2, 3, 4, alpha, and beta. So to figure out what it looks like when we've got substitution on the diene or the ethylene, we look at what's attached to carbon 1. That's still going to be there. Whatever's attached to carbon 2 and 3 will be there. And then whatever's attached to alpha and beta will be there. Now with alpha and beta, because this is a cyclohexene, if there's cis in the starting dienophile, they're going to be cis when we finish. If they're trans, so let's say we flip this over here, they're going to be trans in the final cyclohexene. The only two major complications. One, when we have attack on this first carbon, it can go either way, so it can be up or down. The second is that if we have an asymmetric dienophile, so in this case, beta has a methyl, but the alpha doesn't, we'll get both, because alpha and beta can be flipped in this case. That kind of help you out? Going backwards, it kind of works the same way. Look at your cyclohexene. Wherever you see that double bond, this is the second and third carbon in the diene. And then this will be attached. Whatever's above it, you're just going to write up here with a double bond. Whatever's below it, you can write down here with a double bond. And whatever's opposite that double bond, that's going to be your dienophile. Okay, you see it? Let's see if we can reverse engineer one then, because I'm not getting a lot of questions this morning. So let's go backwards. Let's say we want to figure out what DielsAlder reaction it took to make this happen. The tip off that this is a DielsAlder reaction is that you have a cyclohexane, 6 carbons, with an alkene in it. So give you a minute, try to backtrack out what the diene is and what your dienophile is. And then post a comment when you think you figured it out. While you work on it, I'm going to clear the board up just a little bit. You got it? Okay. So we'll figure out where the diene, wherever that double bond is, that's our second and third carbon in our diene. We can arbitrarily pick which is 1 and 4, which is why we can get multiple products with DielsAlder. So let's say this is 1, this is 4. There's nothing attached to these, but there is a branch coming off the tube. So this would have been our starting diene. What's opposite are alpha and beta carbons. So each one has a methyl. I haven't drawn them with stereochemistry, I should have. But let's say they're both cis. In this case, we've got the methyl group. And because they're both cis, they're going to be cis in the starting alkene. So this would have been our starting dienophile. This would have been our starting diene. And we got that. In that group there. Now, what your book does not talk about, and this is a very practical aspect of DielsAlder, this is also a dienophile. So this can turn around and react with this, and it can react with the next one, and the next one, the next one, the next one. We end up getting these massive polymer chains. Oh, so if the groups are trans, so let's say they look like this, then they're just going to be trans in the starting dienophile. So they preserve that cis-trans relationship after the DielsAlder reaction. So if they're cis beforehand, they're going to be cis afterwards. If they're trans beforehand, they're going to be trans afterwards. Now, it's complicated if you don't use a numbering system. And the big thing I don't do that I think your book does is that it uses numbers on the diene as well as the dienophile. And that's why I use the letters and numbers so I can keep track of which one is which. Because I think it has 1, 2, 3, 4, and it does like 1 in one color and 2 in a different color over here. You had E and ethylene. Let me bring up the discussion board really quick. Okay, let's see what I gave you. So give me a minute just to clean out the board, and we'll talk about the discussion board. So in the discussion board, you're reacting two compounds. Compound A and compound B. And I'm going to rotate compound B to make it a little bit more obvious what's going on. E and ethylene. Hold on, I might be looking at the wrong problem. Just a minute. Oh, I'm sorry, product E and ethylene. Sorry, I misread your question. You're actually asking about what I'm doing. Okay. don't know if anyone's actually figured this one out yet. We want to make it into this compound here. So the 2 steps it takes to make this compound. So, how to tell you without telling you how to do it? You want a hint for step 1 or step 2? Malik's really like weighing it right now. Is like, which step's probably the harder step? Step 1. The worthless hint is that it's going to require a catalyst. And there's lots of catalysts you could choose from this reaction, but they're all the same reaction. Now the other hint I will give you, these 2 rings are actually these 2 rings here. So the only thing you're changing in step 1 is this connection here. But as for step 1, there's a bunch of catalysts that will do it, but you need a catalyst. That'd be nice. Step 2 also requires a catalyst. All right, what other questions you got for me this morning? Any guess on what that catalyst is? Sorry, reading back Malik's comment. She thinks she's figured it out. I was like, any guess what that catalyst is going to be? Of course, she wants the 5 points for herself too, so maybe she'll give you misinformation. the platinum reaction. So I'm guessing this is hydrogenation of alkenes. Actually, this is an interesting, for me, it's an interesting reaction because actually Lewis theory doesn't predict any of this will happen. So in the ongoing dispute between the inorganic and the organic chemist, this is one of the ones that we won against the organic chemist. So we'll start with ethylene. It's a really simple molecule, but they all kind of work the same way with platinum. So we have ethylene and we have a platinum catalyst. And generally in the platinum catalyst we have hydrogen absorbed to the surface. Now, what Lewis theory does not predict are what are called anti-bonding orbitals. So if we look at the orbitals of ethylene, there are actually pi bonding and pi anti-bonding orbitals. So this double bond here really got a lobe on top and a lobe on bottom. And what the platinum will do is it will donate its electrons into the ethylene and donate it into the antibonding orbitals. So what the ethylene actually looks like on the surface is this. So it actually ends up breaking this double bond when it adheres to the surface. Then the hydrogen that's adhered to the surface of the platinum will form a bond with a platinum, and we end up hydrogenating. Oops, wrong side. We end up hydrogenating that double bond. Now, platinum's a bit of a, it's a sledgehammer. Any double bonds, any triple bonds, any unsaturated carbons you have in there are going to get completely saturated with hydrogen when the reaction's done. The big thing here is this is what's called a syn or same side addition. So let's say we had stereochemistry associated with this ethylene. So instead of just simple ethylene, this was a dimethyl 2-butene. When we add the hydrogens, they're going to get added to the same side. So in this case, if we were to draw the stereochemistry, the hydrogens would be on bottom, and our methyl groups would get lifted up. Now, in most cases, this probably is not going to affect anything, but particularly if you end up creating chiral centers when you hydrogenate, you're going to have to keep that in mind that the hydrogens are added to the same side of the double bond. And then from there, you're going to have to figure out what stereochemistry you actually end up with. No, I'm not an organic chemist. I'm still an electrochemist and an inorganic chemist who's teaching organic chemistry. There's a big difference. I'm not an organic chemistry. Do not let me in with them. Nice try, Claire. of you are actually in this chat room this morning. Apparently 8. Simmons-Smith reaction. Okay. Clean off my jury-rigged whiteboard. There we go. So the symptom of a Simmons-Smith reaction, or what you're trying to produce, is a cyclopropane. And let's say we got hydrogen going back. So for the Simmons-Smith, we need an alkene. And we need CH2, I2, on top of zinc. Now, I'm not going to try to pretend I actually remember the mechanism. If you want to know the mechanism, go back and look at the notes. But what happens is that the zinc forms a complex with the diiodomethane, and this zinc also connects to the alkene and inserts the methyl group. Now, the big thing is that this is a syn addition. It's on the same side. So if we were to take this cyclopropane and turn it on its side, so we're going to try really hard to see that. H3, CH3, hydrogen, hydrogen, with our CH2 coming out of the board towards you. In terms of the Simmons-Smith, if you look down that cyclopropane, anything that's on the left side is going to be cis when we backtrack out the alkene. Anything that's opposite is going to be trans in the starting alkene. So our alkene is going to be everything minus that CH2 group that's added from the zinc. So we've got our alkene. Since the methyl groups are on the same side, they're going to be cis. Since our hydrogens are on the same side, they're going to be cis. And that'll be your starting alkene. So the whole reason for using Simmons-Smith is that we want to make cyclopropane. If we want to know if we use the Simmons-Smith, if you see a cyclopropane, unless that was in your starting molecule, odds are you did the Simmons-Smith reaction. And by the way, feel free to ask any questions about earlier material. Like, it's important. So organic chemistry is one of those few courses where the professor says, hey, it builds on itself. They're not like saying that so that you won't forget it for the final exam. It literally does build on itself. We'll constantly go back to older reactions. And hopefully you're seeing this with the synthesis stuff. Olefins, we still need to use EZ. Yes, olefins are just a trade name for alkenes. So I don't know if I put that in the notes. If I did, I apologize. It's just a very old term for alkenes. I had to use it for my early thesis work where I was doing olefin metathesis, and I did having 2 bachelor's degrees and sitting in someone's office like, oh yeah, olefins, I totally know what those are. And I had to ask one day, like, what in the world is an olefin? It's an alkene. It's just a very old name for an alkene. But again, when it comes to the EZ, we're only working with like monoenes. We're not going to do dienes and trienes. I had an inorganic chemistry professor once that said there's a class of compounds called alpos, aluminum phosphates. He had no idea what they were when he interviewed for a job, so he was like, yeah, Alpo, I totally know what that is. Yeah, and he's like, yeah, I thought it was a dog food for a long time, but... Three bromo, 2 pentene with B2H2 glycine. Oh, okay. Yeah, we can solve that. Two pentene. Reaction we're working in is B2H6 followed by H2O2 and sodium hydroxide. So some clarifications, diglyme is just a solvent. So if you're curious why it's in there, it's just the solvent of choice for doing this particular reaction, mostly because the B2H6 is unreacted with it. It is an anti-Markovnikov reaction, so when we add, we're adding the OH group to the opposite side. The big thing here is that typically when we're looking at anti-Markovnikov reactions, they're usually anti-additions, or there's no stereospecificity. There is actually stereospecificity with this one. So once we see this, 2 things we're doing. We're making an OH, and it's going to be an anti-Markovnikov reaction, and it's a syn addition. So the reason why this question is being asked is that do you recognize that 1, it's going to be anti-Markovnikov, 2, that the bromine and the water OH groups are going to be opposite of each other when we add it. So if we look at this reaction, what we mean by anti-Markovnikov is that when we add the functionality or when we add something to this double bond, the nucleophile, either the halogen or the OH, is going to be added to the less substituted carbon. So in this case, the OH is going to go here. We're going to add an H here, and they're going to be to the same side. So when we work it out, 2, 5. The bromine is going to get pushed down, and the OH is going to be up. Now, we'll actually get both because it can add to either side of this. The big thing here is that if this were a ring, the bromine and the water would be trans to one another. So this would give us 3 bromo, 2 pentanol, and we would have to do the RS here for whatever the 2, 3 positions are, but that's how you would work it. What I will do after this video, I did it for my Chem 2, I forgot to do it, may have forgotten to do it for y'all, is go ahead and just release the answer key for those practice packets so you got them on hand. Because it's not like we're going to be working these in class, so. Make a little bit more sense, Nicole? Personally, and I think you're free to agree, I think by the time you get to alkenes, this starts making a lot more sense because you've had so much experience with the stereochemistry, you've had so much experience with the naming that it's easier and easier to learn each successive reaction. Plus, we're also kind of getting to reactions where the mechanism's like 20 pages long, so we're just going to kind of skip the mechanism and kind of more focus on the end result. do B2H6 and H2O2 react with the pentane at the same time? Actually, they don't. So the B2H6 forms basically a ring. As an intermediate, and then the H2O2 and the sodium hydroxide knock it off. And that's why we have them in two separate steps. Step 1 is to form this ring, and step 2 is to decompose the ring into the alcohol. Does Cl2 minus light always create geminal chlorines? I don't think you mean minus light, I think you mean plus light. So if we have Cl2 plus the light to generate the free radicals, what's going to end up happening is if we add too much Cl2, and this is kind of the hard part about free radical reactions, is they're hard to control, you always replace the most substituted carbon. So clear off a little bit more space on the board. So let's say we have something simple like cyclohexane. And we add a half equivalent of Cl2 and light. Well, there's no preference for one carbon over the other because they're all secondary carbons. So the first substitution occurs pretty selectively, but let's say we add more Cl2 and we add more light. Well, the chlorine here is going to want to replace the most substituted carbon. In this case, this is a tertiary carbon. So we end up getting replacement here. So again, this is kind of the issue with free radical treatment of organic compounds. They're very hard to control. So we typically work with low concentrations of like Cl2 or Br2 to kind of keep it selected. But generally, once they replace one carbon, they're going to keep replacing that carbon unless it runs out of hydrogens, because it ends up, the more we replace it with a halogen, the more substituted it becomes. So the more selective it becomes for that free radical halogenation. Pi back bonding. So how they, it's another fun thing that's not really predicted by Lewis theory. So talk about pi back bonding for just a minute. So to understand pi back bonding, it's actually kind of useful to see where that pi notation comes from. So organic molecules, we have sigma bonds and we have pi bonds, and the reason why we call them that is that they're analogous to s and p orbitals. So an s orbital has no nodes, a p orbital has one node. So if we look at a sigma bond between two atoms, the electron density is continuous between the two, so we call that a sigma bond because it looks like an S. So the Greek letter for S is sigma. Your pi bond has a gap. And so with pi bonds, they look like P, and the Greek letter for P is pi. So the thing about p orbitals is they can overlap. And so when we add them together, we end up getting something that looks like that. So when it comes to pi back bonding, what happens is that if we have any type of alkenes, their pi bonds look sort of like p orbitals. So if we were to draw the electron density, it would look like that. And because they look like p orbitals, they can act like p orbitals, and their wave functions will overlap and they share electrons. So this is where pi back bonding comes from, is that the p orbitals can act like the pi bonds can act like p orbitals, interact with each other, share electron density, and that's how they actually kind of form sort of like bonds with each other. This is also why DielsAlder works, is that if we look at the DielsAlder reaction, or we look at the diene and the dienophile in terms of electron density, all the they look like three p orbitals sitting next to each other, so they overlap and form one continuous bond through their p orbitals. So for the DielsAlder reaction, basically all your pi bonds form a bond with each other first, and then we get that rearrangement. So for characterization, carbon NR versus 1NHR, what we need to know. The big thing is more the chemical shifts. When we actually start working with the carbon-13 NMRs and the hydrogen NMRs, they're actually more de-shielded because the pi bonds actually create their own magnetic field, which counters and amplifies the magnetic field. The IR and the mass spec aren't that useful simply because to go from an alkane to an alkene, you're losing two hydrogens. That's a change of two AMUs. Hard to see in the mass spec. The IR, there are bending modes associated with alkenes. They typically are very small, very narrow peaks, and they're hard to resolve. So for the 1H, just recognize that you're more de-shielded than you are for an alkane. So alkanes are typically 0 to 2 ppm. Alkenes are going to be more 2 to 4 ppm. It's going to affect your splitting pattern. They still do the J coupling, but this is where you're going to get more like doublets because you have hydrogens that are isolated because of the alkene. And for the carbon-13, it's also kind of the same story. You get more de-shielded. This also kind of points out a limitation of characterization as well. You kind of need to have some guess as to what you're working with. It's not like you can put it through these 4 techniques and go, oh, this is what I have. You kind of need an educated guess. So with our reactions, we will look at what are potential side products and say, okay, we're going to narrow down what it could be and then see what's consistent with the characterization. But characterization just can't tell you blindly what you have. You need a lot more information. You need some context on the reaction. Start clearing off the board for the next question. Alex done. She's going to go home now. Yeah, the goal this week is to get some whiteboard sheeting to put down on this board. It's worked in the demo, but it's not working so great right now and didn't work too well yesterday. So the question got to ask, SN1, do you favor the protic high dielectric constant solvents and SN2 with aprotic low dielectric? That's correct. So SN1 is going to go through the carbocation intermediate. You can stabilize that two ways. One is you can stabilize it with a high dielectric constant solvent. This means that inherently high dielectric solvents do a very good job of stabilizing charges. What the protic does is that the protic kind of occupies your attacking nucleophile. So usually your nucleophile is an anion, the hydrogen attaches to it to neutralize it, so it kind of gives you time to form the carbocation. For the SN2, you're not trying to create the carbocation, so by doing a low dielectric constant solvent, you've really made a very unfavorable condition for a charge to even be formed. The aprotic also guarantees that the nucleophile is available to react. So again, your nucleophile is typically an anion. If there's no hydrogen to attach to it, it's more likely to participate in the reaction. By the way, Terry, thank you for that link to the POCL3. I've actually added that to my lecture notes for this fall. So they had the POCL3, they have an example of the POCL3, and they have an explanation in the notes to how the POCL3 works. It was good. You learn something every semester, right? The one thing we are going to try, so we have a new organic instructor starting this fall in North. She's not going to try to coordinate to make sure that for chemists, for Orgo 1, we're teaching the same reactions. So this one, anyone that goes between North and South Campus, there's at least a list of reactions to say, like, you should know how these work. So if for whatever reason you need to shift between campuses, you're going to have that continuity. You know that you're going to be at least, you're going to have the reactions in hand to be able to do the synthesis they're asking you to do. All right, since you want to ask questions, I'll ask you questions. Have you found the discussion boards helpful so far? You're either afraid to respond or there's just that bad a lag in this video. Good. One person likes it. All right, 2 people think it's helpful. Class of 10, that's 20%. I would say that's good. My Chem 2 students asked about y'all. I wanted to know how organic was handling this because they're struggling. I mean, it's honest. They're shifting to an online course. And honestly said, y'all actually have a little bit easier because you don't have any labs to make up. They're actually having to do virtual labs. They're having to do lab reports and submit them. Y'all are just doing discussion boards. I'm going to see what's going on with the streaming software I'm using. It's my first time using it. Probably should have messed around with this earlier, but hopefully we can decrease the lag time. It probably also doesn't help the school gave me the absolute cheapest computer they could find to do this, which I totally get why, but my desktop computer can handle it, but I'm not dragging it into my spare bedroom. So kind of the bind we're in. And I'm not, my computer's actually in my bedroom, so I'm not going to stream from there. I will say your discussion boards were actually the hardest to write. The big thing was drawing the figures and making sure that they were visible and going through and making sure that we were covering all the reactions that you need to know. It was a challenge figuring out what to do for y'all with the labs, and there is going to be a practical. It's similar to what you would have done. From what I understand with organic chemistry, there's a hands-on practical and there's a paper practical. You're getting the paper practical. But as you'll see in the discussion board for the week before the lab practical, I'm going to list what types of questions are going to be asked, specifically what concepts. And any questions you have, just ask them and I will answer them on the discussion board. And if you don't have a question, just say, I don't have a question, just so I can mark you for the attendance. Now, I will say they do have a cool titration lab to do in Chem 2. It's actually a virtual lab that you have to measure the pipette, you have to put it into the beaker. And I liked it because I was trying to rush through the demonstration and it punishes you for trying to rush through. So it is a good program. It really annoyed me because it wouldn't let me rush through and do sloppy work. You actually have to make sure the pipette's at the correct line. You actually have to condition the pipette before you use it. It's really cool. It's just not very good if you're trying to rush through it and see what all is involved. But yeah, I was trying to find, there was actually online software that's actually a virtual lab that you go through with hands and do things. And for the low price of a lot of money, you too could do these demonstrations, but I wasn't going to even begin to ask you guys to pay for an online lab service. All right, so I think we're kind of dying down with the discussion. So there's another live stream posted to the updated announcement. So I'll be back online Thursday. Hopefully we'll have the issue of the lag resolved with the software by that point. I got one more live stream to figure it out. And in terms of the lab today, I'll be available through Teams if you've got questions during the normal lab period. Other than that, I will see you all Thursday.